There is a place that belongs to our solar system but has never felt the sun's warmth. It surrounds us in every direction at distances so vast that light itself needs more than a year to cross it. Inside it sit hundreds of billions, perhaps trillions, of frozen objects drifting in darkness so complete that the sun appears as nothing more than one bright star among millions. Some of those objects are 4.6 billion years old and have never moved until a passing star disturbs them and sends them falling inward, where we watch them streak across our skies and call them comets. This is the Oort Cloud. It is the last place in the solar system. It is the first place no human being will ever reach, and it is the most dangerous frontier in the history of exploration. If this journey into the dark edges of our solar system, taking a moment to like this video and subscribe to the channel, means the world to us, make yourself comfortable and find a good position to rest in. In 3, 2, 1, liftoff. There is something almost restful about watching a comet. People have been doing it for as long as there have been people standing in fields and on hillsides and on the decks of ships, tilting their heads back and watching that slow, silent smear of light move across the dark. The ancient Chinese kept careful records of them. The Babylonians did the same. In 1466, a comet appeared that was so bright and moved so slowly that crowds gathered in European cities, believing the end of the world had arrived. When Halley's Comet returned in 1910, the newspapers ran stories explaining that Earth would pass through its tail, and some people genuinely prepared for the worst. And when the comet now called Hale-Bopp hung in the sky in 1997, visible to the naked eye for an extraordinary 18 months, millions of people stepped outside on clear evenings just to look up. That is the thing about comets. They feel personal. They feel close. They arrive in the part of the sky that belongs to us, the same sky we watch for weather, the same sky we learn the constellations in, the same sky that has always been the ceiling of human experience. When a comet appears in that sky, it seems to be right there with us, a visitor that has come to call. But here is the truth that changes everything. That visitor has been traveling for a very long time, longer than any human civilization, longer than our species, longer, in many cases, than the continents have held their current shapes. The comet you watched streak gracefully across your sky has been falling toward the sun for tens of thousands of years. And it did not begin its journey anywhere near us. It began its journey at the very edge of the solar system, in a place so far away and so dark and so cold that we have never once seen it directly. A place that surrounds us on all sides, a frozen graveyard the size of a small galaxy in its own right, hanging silently at distances that break every analogy you might reach for. And the story of how we came to know it exists is one of the most remarkable quiet triumphs in the history of science. To understand how anyone ever figured this out, you have to go back to a problem that astronomers had been sitting with for generations. Comets burn. That is simply what they do. Every time a comet swings through the inner solar system and passes close to the sun, the heat vaporizes some of its ice, jets of gas and dust stream outward to form that beautiful glowing tail, and a small but real amount of the comet is consumed. A comet that makes repeated visits to the inner solar system is slowly dying. The math was never kind. Most short-period comets, the ones that loop around relatively quickly, like Halley's Comet, with its roughly 76-year cycle, have at most a few thousand more orbits left in them before they are used up entirely. In cosmic time, a few thousand orbits is barely a breath, and yet the sky keeps producing new ones. Not just tired, half-burned comets on their 1000th pass, but genuinely fresh ones, bright, pristine, packed with ice and volatile material. arriving on orbits that take them hundreds or thousands of years to complete. Where were they before? You cannot have been around since the solar system formed and still be that fresh, that cold, that untouched, if you have been spending any meaningful portion of your life anywhere near the sun. Something had to be storing them somewhere. Something had to be keeping them cold and still for billions of years, and then letting them go. By the middle of the 20th century, this was not a minor puzzle. It was a genuine mystery at the heart of solar system science, and the man who solved it was a Dutch astronomer named Jan Oort, and one of the most quietly transformative figures in the history of astronomy. Oort had already spent decades reshaping how scientists understood the Milky Way. He had confirmed that our galaxy rotates, that the sun is nowhere near its center, and that the distance from our solar system to the galactic core is roughly 30,000 light-years, a number that is still used today. He had built the foundations of what would become radio astronomy in the Netherlands. By the time he turned his attention to the problem of comets in the late 1940s, he was already one of the most respected astronomers alive. What Oort did was go back to the data. He studied the orbital histories of 19 long-period comets, comets with orbits stretching to enormous distances from the sun, and he looked specifically at the farthest points those orbits reached, the places where each comet had been before it began its inward fall. What he found was a spike, a clustering of those farthest points around distances of roughly 20,000 to 50,000 astronomical units from the sun. 1 astronomical unit is the distance from the Earth to the sun, approximately 93 million miles. 20,000 astronomical units is 20,000 times that distance. 50,000 astronomical units is 50,000 times that distance. And yet, multiple comets, arriving from entirely different directions, were tracing their origins back to that same enormous range. Oort published his findings in 1950 in a paper titled "The Structure of the Cloud of Comets Surrounding the Solar System and a Hypothesis Concerning Its Origin," written for the Bulletin of the Astronomical Institutes of the Netherlands. It is not a dramatic document to look at. It is patient, methodical, and careful in the way that the best science always is. But its conclusion was extraordinary. Oort proposed that a vast, roughly spherical shell of icy bodies surrounds the entire solar system at these enormous distances. Not a flat disk like the asteroid belt or the Kuiper belt, but a sphere that encloses the solar system on all sides, like the rind of a piece of fruit. Now and then, that shell gets disturbed. A passing star drifts too close. The gravitational tug of the galaxy itself, bearing down from the galactic plane, shifts the orbit of some frozen body just enough, and something that has been sitting perfectly still in the dark for billions of years begins, slowly and inexorably, to fall. That falling takes a very long time. Some comets that reach the inner solar system have been falling for tens of thousands of years before they finally arrive. They have traveled across distances that make the gap between Earth and the sun look like a crack in the sidewalk. They arrive on their first and often only visit, burn briefly near the sun, and then either swing back out again or disintegrate entirely. And then the sky is dark once more, and the cloud waits, holding billions more, in silence. What Oort described became known as the Oort Cloud. Scientists have never seen it directly, not once. Our most powerful telescopes cannot resolve individual objects. At that distance, they are simply too small and too dark and too far away. There is no photograph of the Oort Cloud in any archive anywhere. Every image you may have seen is an artist's concept, a model, an extrapolation. The Oort Cloud is inferred, deduced, reasoned from what we can see from here, the way a detective might reconstruct a crime from the evidence left behind. The comets are the evidence. Their orbits are the fingerprints. And the cloud they point back to is as real as anything astronomers have ever deduced, not in the sense of being touched or photographed, but in the sense of being the only explanation that fits everything we observe. That distinction matters, and this video will honor it throughout. The Oort Cloud is theoretical but scientifically accepted, which is a very different thing from speculative or uncertain. There is no serious competing explanation for where long-period comets originate. There is no rival hypothesis that has withstood the decades of scrutiny that Oort's idea has withstood. When scientists speak about the Oort Cloud today, they are not speaking about a guess. They are speaking about the best supported model for the outermost structure of our solar system, a model that has survived every comet orbital analysis ever conducted since 1950. The uncertainty is not about whether it exists. The uncertainty is about its exact dimensions, its precise population, its internal structure, and the mechanics of what happens to it when the universe decides to push. To understand why exploring this place is not just difficult, but almost incomprehensibly so, you need to build the picture from the inside out. You need to know what came before. You need to feel what we have already crossed before you can understand what has not yet been crossed. Start with the moon. On a clear night, the moon is the brightest object in the sky. It is close enough that we can see craters and mountains and dark plains with nothing more than a backyard telescope. The distance from Earth to the moon is roughly 239,000 miles. It took the Apollo missions approximately 3 days to get there. 3 days. For the entire span of human space exploration, the moon was the farthest any human being had ever traveled, and it was 3 days away. Now move outward to Mars. The red planet sits between 35 million and 250 million miles from Earth, depending on where both planets are in their orbits. The fastest spacecraft ever sent to Mars took approximately 7 months to arrive. 7 months of travel to reach a world that shares our neighborhood in the solar system. And yet Mars, even at its farthest, is still inside the inner ring of the planetary family. Move farther out. Jupiter is on average roughly 5 astronomical units from the Sun. Saturn is about 10 astronomical units. Uranus is around 19. Neptune, the outermost of the 8 recognized planets, orbits at approximately 30 astronomical units from the Sun. The Voyager 1 spacecraft, launched in 1977, flew past Jupiter in 1979, past Saturn in 1980, and then used Saturn's gravity to slingshot itself up and out of the ecliptic plane, heading away from the Sun at roughly 38,000 miles per hour, faster than any other human-made object in history. It has been traveling at that speed for nearly 50 years. As of 2026, Voyager 1 is approximately 172 astronomical units from the Sun, 172 times the distance from the Earth to the Sun, after nearly 5 decades of travel without stopping. That number deserves to sit quietly for a moment. 172 astronomical units. Voyager 1 is the most distant object humanity has ever placed in space. It crossed the heliopause, the boundary where the Sun's solar wind gives way to interstellar space, in 2012. It is, in every meaningful sense, the farthest we have ever gone. The inner edge of the Oort Cloud begins at roughly 2,000 astronomical units. Some estimates place it even closer, around 2,000 to 5,000 astronomical units, where the disc-shaped inner region known as the Hills cloud begins to shade into the broader spherical outer shell. But by the most conservative mainstream estimate, the Oort cloud starts at 2,000 astronomical units. Voyager 1, after 49 years of travel at speeds no human vehicle has ever matched, is at 172 astronomical units. It has covered less than 9% of the distance to the inner edge of the cloud that surrounds us. At its current speed, Voyager 1 will reach the inner edge of the Oort cloud in approximately 300 years, and it will not exit the far side of the outer cloud for approximately 30,000 years. The spacecraft's nuclear power source, which allowed it to send data home, ran out of useful power around 2025. Voyager 1 is already functionally silent as an instrument. It is a piece of metal coasting through space on momentum alone, carrying a golden record and the handprints of everyone who built it, and it will not reach what we are talking about tonight for 3 centuries. When it does arrive, no one will hear it. This is the first thing you need to understand about the Oort cloud. It is not the edge of the solar system in any casual drive to the horizon sense. It is something of an entirely different order. The distance from the Sun to Neptune, the distance that already felt impossible to cross in a human lifetime, is 30 astronomical units. The outer boundary of the Oort cloud is estimated at somewhere between 50,000 and 100,000 astronomical units, and some models push it as far as 200,000 astronomical units. We are talking about a structure that is, at its outermost reaches, at least 3,000 times farther from the Sun than the outermost planet. But here is where it stops being merely a number and starts being something you can feel. The outer edge of the Oort cloud is estimated to lie roughly 1/4 to halfway between the Sun and the nearest star Proxima Centauri, which sits approximately 4 light-years away. The Oort cloud reaches out so far that it begins to blur into the space between stellar systems. At that distance, the Sun is no longer a warm, dominating presence in the sky. It is a bright star, still the brightest, still clearly the gravitational anchor, but a star among stars, and not by very much. Think about what that means for a comet sitting out there. It formed in the warmth of the early solar system, near the giant planets, jostled and kicked outward by Jupiter's enormous gravity over millions of years, drifting slowly to this frozen outpost at the Sun's gravitational reach. It has been sitting there for 4.6 billion years. The temperature out there is estimated to be somewhere around -440 degrees Fahrenheit, close to absolute zero, the lowest temperature physics permits. It has never been warmed. It has never been lit. The Sun provides less illumination at that distance than a full moon provides to Earth. It is dark in a way that has no human reference. And it is going to stay that way unless something comes along to disturb it. That disturbance is not rare. It is not an unusual event. It is one of the defining rhythms of the outer solar system, operating on timescales so long that human civilization cannot even serve as a useful comparison. The galactic tide, the cumulative gravitational pull of everything in the Milky Way, operating on the outer cloud, acts constantly, warping orbits slowly and gently the way ocean tides warp water. Over millions of years, this tidal force nudges some fraction of the cloud's population onto new trajectories that curve them inward. And, passing stars, other suns drifting through the galaxy in their own long orbits, occasionally draw close enough to the outer cloud to disturb it as well, sending additional objects falling toward the inner solar system. Most of these new comets will take tens of thousands of years to arrive. Some will take hundreds of thousands. And when they do arrive, they come as strangers. They have never seen the sun as more than a distant light. They have never been warmed, never had their volatile ices sublimated into the kind of brilliant tail that makes comets so visible. They arrive fresh, cold, chemically intact, carrying the original recipe of the solar system's raw materials, preserved in deep freeze since before the Earth existed. This is why the scientific community has never stopped caring about comets, even after centuries of watching them. Every long-period comet that falls into the inner solar system is a message from an almost unimaginable distance and an almost unimaginable age. It is not just pretty to look at. It is a sample. Now consider the scale of what is producing these samples. The outer Oort cloud is estimated to contain at least 1 trillion objects larger than 1 kilometer in diameter, and approximately 1 billion objects larger than 20 kilometers across. The spacing between objects is extraordinary, averaging perhaps tens of millions of kilometers apart, so that despite the vast number of bodies present, the cloud is extraordinarily sparse. If you could somehow position yourself inside it and look around, you would not see a dense field of ice and rock. You would see darkness in almost every direction, with individual objects separated by distances that would take years to cross at the speeds of any ship we have built. The Oort cloud is not crowded. It is immense. That distinction, not dense but vast, is one of the keys to understanding why it is dangerous in the particular way that it is. When people think of space exploration facing physical obstacles, they often imagine asteroid belts, the way science fiction films have depicted them: crowded, treacherous, almost deliberately designed to destroy ships. The actual asteroid belt is nothing like that. You could fly through it without seeing another object. The Oort cloud is similar in that respect. The risk does not come from navigating through a dense field of debris. It comes from something much harder to manage: the fact that the objects are there. They are moving, they have no organized orbital plane, and they cannot be charted. In the Kuiper belt and the main asteroid belt, objects orbit in a relatively flat disk, roughly aligned with the plane of the planets. That means you can know where they are likely to be. You can map them. You can predict. The Oort cloud objects orbit the Sun from every possible direction above and below the ecliptic, at every conceivable inclination, in orbits so long that they spend most of their existence far beyond any observation we could ever make. There is no map of the Oort cloud. There never will be a complete one. A spacecraft traveling through it would be navigating through a space populated by objects it could not track or predict, arriving potentially from any direction in a darkness too deep for radar to be fully trusted. This is the nature of the frontier that Oort described in 1950, not a wall at the edge of the solar system, but a vast, invisible, spherical enclosure, holding within it both the record of our origins and the seeds of our most ancient catastrophes. The comets it produces have been arriving in the inner solar system throughout Earth's entire history. Some of them have struck the Earth. Some of those impacts were small. Some were not. And the processes that produce them have never stopped and will never stop for as long as the Sun continues its journey through the galaxy, and passing stars continue their slow drifts through the neighborhood, and the galactic tide continues its patient geological pull. What Oort gave us in that 1950 paper was not just an explanation for where comets come from. He gave us the true dimensions of the solar system, dimensions that had been hiding in plain sight for as long as people had been watching the night sky. Every comet that anyone had ever seen, From the great comets of ancient history to the ones your grandparents may have pointed out to you when you were small, was a messenger from this place. The solar system did not end with Neptune. It did not end with Pluto, discovered in 1930 and regarded for decades as the outermost known world. It extended outward, spherically, in every direction, to distances that could not even be compared meaningfully to anything else in the solar system. Oort himself was a careful man. He did not overstate his case. He framed his 1950 paper as a hypothesis, clearly noted the indirect nature of his evidence, and acknowledged that direct confirmation was not possible with any technology then available. He died in Leiden in November of 1992 at the age of 92, having lived long enough to see his hypothesis become the organizing framework for everything scientists understood about long-period comets without ever living to see the cloud photographed. He never expected to. He understood, better than anyone, how far away it was. What he had given the world was a map to something that could not be mapped, a conceptual framework for understanding the outermost reaches of our solar system, built from nothing more than the patient, meticulous analysis of the orbits of 19 comets. It is the kind of achievement that looks simple in retrospect, and was anything but, and the place it revealed, the frozen shell surrounding us in every direction at distances that collapse the meaning of every previous unit of measurement we used, is the subject of this video. Because there is something else about the Oort Cloud that the distance alone does not fully convey. The distance makes it unreachable. But it is not just unreachable. It is also, in ways that will become clear as this journey continues, the most genuinely dangerous frontier any explorer could ever face. Not dangerous in the way that early ocean navigation was dangerous: bad weather, inadequate instruments, the risk of running aground. Dangerous in ways that are built into the physics of the place itself. Dangerous because of what lives there, what moves through it, what governs it, and what the universe occasionally sends through it with no announcement and no warning. The comets that reach us are the friendly ones, in a manner of speaking. They fell inward alone, on their own long arcs, one at a time, over tens of thousands of years. There are mechanisms by which they come in clusters. There are processes by which the cloud can be stirred in ways that send not one, but waves of them inward, across timescales of millions of years. The record of those waves is written into the geological and fossil record of this planet, in the pattern of impact craters, in the boundaries between epochs in the history of life, in the moments when the living world was interrupted in ways that took tens of millions of years to recover from. The Oort Cloud is the most distant place in the solar system. It is the first place in what is almost interstellar space. It is a frozen archive of everything that existed before the planets formed. And it is, by any measure that can be fairly applied, the most dangerous frontier in the history of exploration. Later in this video, we will walk through exactly what makes it dangerous in ways that go far beyond simple distance. For now, let the scale alone settle in the scale of a place so vast that the most distant object humanity has ever launched will not even reach its threshold for 3 more centuries, and will take another 30,000 years to cross it. That is the Oort Cloud. That is where this journey begins. The solar system, as most people learned it, has a shape. It is a flat disk, the sun at the center, the planets arranged in their lanes around it like runners on a track, everything moving in roughly the same direction and in roughly the same plane, the whole arrangement tilted just a little against the larger backdrop of the galaxy, but essentially a single organized sheet of matter and motion. That picture is correct as far as it goes, but it describes only the inner neighborhood, the busy, well-lit part of the solar system where the planets formed and where most of the action we have ever observed takes place. It describes maybe the innermost 2 or 3% of what actually belongs to the Sun. The rest is the Oort Cloud, and it does not look like a disk at all. To understand the structure of what surrounds us, you have to let go of the flat image entirely. The Oort Cloud is not a ring. It is not a belt. Scientists believe it is a shell, or more precisely, 2 nested structures that together form a roughly spherical enclosure around the entire solar system, extending in every direction equally, as complete as the skin of an orange. Above the ecliptic plane, below it, ahead of the Sun in its journey through the galaxy, behind it, in every possible direction out to distances that dwarf everything else in solar system science, the cloud extends. It does not care about the plane the planets share. It does not confine itself to a disk. It wraps the solar system the way the atmosphere wraps the Earth, except that, instead of being a thin layer a few hundred miles deep, it extends for tens of thousands of astronomical units in every direction. Scientists describe the structure of the Oort Cloud in 2 parts. The inner region, sometimes called the Hills Cloud, after the astronomer Jack Hills, who proposed its existence in 1981, is the denser of the 2. It is not spherical, it is more disc-shaped, roughly aligned with the plane of the solar system, thicker than the asteroid belt but still fundamentally flat compared to what lies beyond it. Current estimates place the Hills Cloud between roughly 2,000 and 20,000 astronomical units from the Sun. It is thought to be more densely populated than the outer cloud, and its total mass may exceed that of the outer cloud, but because it lies deeper within the Sun's gravitational reach, the objects there are harder to dislodge and rarely make their way inward as comets. They orbit in comparative stability, feeling the influence of the giant planets at the inner edge and the first whispers of galactic tidal forces at the outer edge. A 2025 research paper even proposed, intriguingly, that the Hills Cloud may not be cleanly disc-shaped at all, but may have a spiral structure of its own, a finding that, if confirmed, would add yet another layer of complexity to an already remarkable place. That work is still being evaluated by the scientific community, but it is a reminder that the inner cloud is still poorly understood even by the standards of a structure that has never been directly observed. Beyond the Hills Cloud, the outer Oort Cloud begins, and this is where the full spherical nature of the structure takes hold. The outer cloud is thought to extend from roughly 20,000 astronomical units out to somewhere between 50,000 and 100,000 astronomical units, and some models allow for its influence to stretch as far as 150,000 or even 200,000 astronomical units before the Sun's gravitational hold finally yields entirely to the fabric of the galaxy. At those outer reaches, the grip of the Sun and the influence of the galactic tide are nearly balanced, and individual objects can be nudged out of their orbits by the gentlest of perturbations, a passing star, a drifting molecular cloud, the slow, patient tidal pool of the galaxy's disk, bearing down from thousands of light years away. What lives in this outer shell is almost impossible to visualize without working through the numbers carefully. Current scientific estimates place the population of the outer Oort Cloud at roughly 1 trillion objects, larger than 1 kilometer in diameter, that is, 1 followed by 12 zeros. There are also thought to be approximately 1 billion objects larger than 20 kilometers across. The total mass of the outer cloud is estimated to be somewhere around 5 times the mass of the Earth, though this figure carries significant uncertainty because no one has ever measured an Oort cloud object directly. That mass figure might seem surprisingly modest for a structure of such enormous volume, and that is precisely the point. The outer Oort cloud is not dense. It is sparse in a way that strains description. Consider this. 1 trillion objects sounds like a crowded place, but spread that many objects across a spherical shell with an inner radius of 20,000 astronomical units and an outer radius of 100,000 astronomical units, a volume so immense that writing it in cubic meters would require a number with more than 40 digits, and the average distance between neighboring objects becomes something in the range of tens of millions of kilometers. The nearest companion to any given Oort cloud body is tens of millions of kilometers away. Not meters, not kilometers, not even the few million miles that separate some asteroids in the main belt. Tens of millions of kilometers in every direction of absolute emptiness. If you stood on one of those frozen bodies and looked around, you would see nothing. You might see the sun, far dimmer than a full moon appearing from Earth. You might see the stars, undimmed by any atmosphere, but you would not see your nearest neighbor. It would be far too small and far too distant, lost in a darkness that your eyes could never penetrate. This sparseness is what makes the Oort cloud so unlike every other populated region of the solar system. The asteroid belt, the Kuiper belt, the region around Saturn's rings, all of these have objects close enough to interact visually with one another, close enough to collide on timescales that matter to geology and planetary science. The Oort cloud is different. Its objects are so widely separated that they almost never interact with each other at all. Each body is essentially alone, orbiting the Sun in near total isolation, responding only to the Sun's gravity and to the vastly slower, subtler forces of the galaxy itself. And what are these objects made of? The honest answer is that scientists have never held a piece of one. Every inference about Oort cloud composition comes from studying the comets that astronomers believe originated there, the long-period comets that arrive in the inner solar system on their first or only passage, their surfaces unaltered by repeated heating. Based on those studies, Oort cloud objects are thought to be icy planetesimals, bodies composed primarily of water ice, frozen carbon monoxide, frozen carbon dioxide, methane, ammonia, and hydrogen, cyanide, mixed with dust and silicate rock. Think of them as dirty snowballs on an astronomical scale, some no larger than a small hill, others potentially reaching tens of kilometers across roughly the size of the object that struck the Yucatan Peninsula 66 million years ago and ended the age of dinosaurs. These are not random compositions. They are the raw materials of the early solar system, the leftovers from the period 4.6 billion years ago when the Sun was young and the planets were forming from the disk of gas and dust that surrounded it. The leading scientific hypothesis for how the Oort cloud formed involves the giant planets, particularly Jupiter and Saturn, whose enormous gravitational fields acted like slingshots during the early solar system. Smaller, icy bodies that wandered into the orbital territory of those giants were flung outward with tremendous speed, some so fast that they escaped the solar system entirely and became interstellar wanderers. Others were flung far, but not quite far enough to escape, and they settled into these enormous, distant orbits, gradually shaped by the galaxy's tidal forces into the spherical distribution we infer today. A proportion of Oort Cloud material may not have formed near the Sun at all. Research has suggested that when the Sun was very young, it formed in a stellar nursery alongside hundreds of other stars, all of them packed close together in a birth cluster before the cluster gradually dispersed over tens of millions of years. During that early, crowded period, material from the protoplanetary disks of neighboring stars may have been exchanged, captured by the Sun's gravity as the stars drifted apart. If that is correct, the Oort Cloud may be partly a library of material from other solar systems entirely, mixed in with our own primordial leftovers, indistinguishable from the outside. The cloud would then be not merely the edge of our solar system, but a repository of interstellar exchange, a frozen record of the Sun's earliest neighborhood. This is part of what makes the Oort Cloud scientifically extraordinary. Those frozen objects have been sitting undisturbed at temperatures estimated to approach nearly -459 degrees Fahrenheit, just fractions of a degree above absolute zero for the entire history of the solar system. 4.6 billion years of deep freeze. Whatever chemistry existed in the protoplanetary disk at the moment those objects were flung outward has been preserved essentially intact. No warmth has altered it. No cosmic ray bombardment capable of penetrating solid ice has reached much of their interiors. The objects in the outer Oort Cloud are, in a very real sense, the most pristine samples of the original solar system that exist anywhere. They are older and less altered than any meteorite that has ever fallen to Earth. They are older and less altered than any comet that has passed through the inner solar system more than once. They are a frozen record of conditions that prevailed before the Earth was fully formed. The problem is getting to them, and that problem is not merely a matter of distance. Distance is only the beginning of it. Let us return to Voyager 1, because it is the most honest measuring stick we have. Launched in September of 1977, carrying scientific instruments so precise for their time that they transformed our understanding of Jupiter, Saturn, and their moons, Voyager 1 is moving away from the Sun at approximately 38,000 miles per hour. It has been doing so for nearly 50 years. It crossed the orbit of Neptune, 30 astronomical units from the Sun, in less than 12 years. It crossed the termination shock, where the solar wind slows as it meets interstellar space, around 84 astronomical units out. It crossed the heliopause, the formal boundary between the solar wind and the interstellar medium, in 2012, when it was about 121 astronomical units from the Sun. At that moment, Voyager 1 became the first human-made object to enter interstellar space in the strict technical sense. As of 2026, Voyager 1 is approximately 172 astronomical units from the Sun. That means that in nearly 50 years of continuous travel at speeds no other human vehicle has matched, we have covered 172 astronomical units. The inner edge of the Oort Cloud is roughly 2,000 astronomical units away. Run that arithmetic. 172 astronomical units in 50 years gives a travel rate of roughly 3.4 astronomical units per year. At that rate, reaching 2,000 astronomical units, the estimated inner edge of the Oort Cloud would take approximately 560 years from now. If Voyager 1 were heading in the right direction and still functioning, neither of which is true, the nuclear power source that allowed Voyager 1's instruments to operate has been fading for years, and the last of its scientific instruments are expected to lose power in the mid-2020s. The spacecraft will coast in silence for centuries before it reaches the cloud. To reach the outer edge, say, 100,000 astronomical units would require, at Voyager 1's speed, approximately 29,000 years. Modern human civilization, as we know it, is only about 10,000 years old. The outer Oort Cloud is nearly 3 times that span of time away, measured in years of travel at the fastest speed any vehicle in history has achieved. This is not a solvable problem with the technology of the next decade or the next century, or arguably even the next several centuries, unless something fundamental changes about how we propel objects through space. A hypothetical spacecraft traveling 10 times faster than Voyager 1, something we are nowhere near building, would still need approximately 2,900 years to reach the inner edge of the Oort Cloud. A spacecraft traveling 100 times faster than Voyager 1, an almost incomprehensible engineering achievement, would need roughly 290 years to reach the inner edge and 3,000 years to cross the cloud entirely. The cloud is not merely distant, it is distant on a time scale that defeats the continuity of any human institution, any government, any civilization, any scientific program that has ever existed. And even if you could solve the travel time, there is a second problem that grows worse the farther out you go, and that problem is communication. Radio signals travel at the speed of light, approximately 186,000 miles per second, the fastest that information can move in our universe. When Voyager 1 was crossing the orbit of Saturn, its signals took about 80 minutes to reach Earth. That was already long enough to be operationally uncomfortable. Any question sent to the spacecraft took 80 minutes to arrive, and any response took another 80 minutes to return, meaning a round-trip communication cycle of more than 2.5 hours. Mission controllers had to plan carefully, anticipate problems, and build in time for delays. At Neptune's distance, the round-trip delay extended to more than 8 hours, still manageable, still within the range of a normal human workday. At 1,000 astronomical units, a single radio signal from a spacecraft to Earth takes approximately 5.8 days to arrive. The round trip is nearly 12 days. If something went wrong on the spacecraft, the mission team on Earth would receive the distress signal almost 6 days after the event, and their response would take another 6 days to return. Whatever was happening would have been resolved one way or another long before any human decision-making could intervene. At 10,000 astronomical units, still well inside the inner Oort cloud, the one-way signal travel time is approximately 58 days, nearly 2 months just for the message to arrive, a round-trip communication cycle of nearly 4 months. Any crew at that distance would be functionally autonomous, making every decision independently, with no possibility of consultation with Earth, no possibility of assistance, no possibility of rescue in any meaningful time frame. At 100,000 astronomical units, the outer edge of what is considered the main Oort cloud, a radio signal traveling at the speed of light, takes approximately 1 year and 5 months to reach Earth. The round-trip communication delay is nearly 3 years. A crew at the outer Oort cloud would send a message home and wait almost 3 years for a response. If they reported an emergency, Earth would not even receive the report for 17 months. Whatever they were facing, they would face it entirely alone. This is not a solvable problem by building better radios or more powerful transmitters. It is a fundamental constraint of physics. The speed of light is the speed of light, and no engineering achievement will ever change it. At the distances of the outer Oort Cloud, the communications window that connects a crew to humanity closes completely. They would be, in every practical sense, on their own, more isolated than any explorer in human history, more isolated than anyone who has ever rounded a cape into an unknown sea or crossed a pole through a winter storm. Those explorers were at least on the same planet, within months of return, with some hope of rescue if things went wrong. A crew at the outer Oort Cloud would be so far from Earth that the concept of rescue would be a kind of poetry, not a plan. There is also the matter of what the sun looks like from out there, and what that means for a crew trying to navigate, to operate solar panels, to feel any psychological connection to the home system. At 1 astronomical unit, Earth's distance from the sun's solar energy is plentiful enough to power spacecraft instruments, heat a spacecraft interior, and provide meaningful navigation reference. At Neptune's distance, 30 astronomical units out, the sun provides about 1/900th of the light it provides at Earth. Still detectable, still directional. At 100 astronomical units, about 1/10,000th of the light at Earth. At 1,000 astronomical units, about 1/1,000,000th. At 10,000 astronomical units, the sun is roughly 100 million times dimmer than it appears from Earth. It is still the brightest star in the sky by a meaningful margin, but it is a star now, not a sun, a bright point of light in a field of other points of light, providing essentially no useful energy to any solar panel ever built, and casting enough light to read by only in the most theoretical sense. At the outer Oort Cloud, if you were somehow there and looked back, you would need to know which star to look for. The sun would be among the brightest stars in the sky, perhaps the brightest, but it would not be obviously the sun. Nothing about it would immediately announce itself as home. You would be in a darkness indistinguishable to any instrument we have today from the darkness between the stars. In a very real physical sense, you would be in interstellar space. None of this is meant to be discouraging for its own sake. It is simply what the place is. The Oort Cloud is not a place that was designed to be explored, because the universe does not design places for exploration. It is a place that formed under the specific conditions of our solar system's early history, took up residence at the specific distances where the sun's gravitational pull and the galaxy's gravitational tide are roughly balanced, and has been sitting there unchanged for 4.6 billion years. Its inaccessibility is not a flaw, it is a description. What makes it useful to us at this distance is not what we can go there and collect. It is what it sends us. Every long-period comet that arrives in the inner solar system is a sample that the cloud has dispatched not intentionally, but by mechanism. It fell inward because something perturbed it, and now it is here, within range of instruments and telescopes, and, in the most favorable circumstances, spacecraft. And the comets, arriving on their very first journey, inward, the ones that have never been warmed, never had their outermost layers altered by the sun's radiation and heat, are the most valuable of all. Their surfaces are the surfaces they had 4.6 billion years ago. Their chemical compositions are the compositions of the original protoplanetary disk. This is why the scientific community has been so eager to reach one of these fresh comets before it has been significantly altered by its first pass close to the sun. It is a problem of timing. These objects arrive on their own schedules, with almost no advance notice, and by the time they are detected and identified as likely Oort Cloud visitors, they are often already well inside the inner solar system, racing toward perihelion at speeds that would require extraordinary mission planning to intercept in time. The dream of studying a pristine comet at close range has been a goal of planetary science for generations. Later in this video, that dream becomes relevant again when we discuss what is being built right now to pursue exactly that. But for now, hold the picture of the cloud itself. A sphere of frozen darkness surrounding the entire solar system, containing approximately 1 trillion icy bodies in its outer region alone, each one a capsule of 4.6 billion year old chemistry, each one separated from its nearest neighbor by tens of millions of kilometers, the whole structure existing at temperatures within a breath of absolute zero, bathed in sunlight, dimmer than the light of an ordinary star, and governed not by the sun's authority, but by the patient geological pull of the galaxy itself. It reaches from 2,000 astronomical units all the way out to distances where the concept of belonging to our solar system becomes genuinely ambiguous. It does not announce itself. It does not move. It waits. What disturbs it is what comes next, and the things that disturb it are neither rare nor gentle. The forces that reach into the Oort Cloud and stir it into motion are some of the most powerful and most permanent forces in the known universe, and their consequences are written into the history of life on this planet in ways that took science a very long time to recognize. Understanding those forces means understanding why the Oort Cloud is not merely a place of extraordinary scientific value, but something far more consequential, something that has shaped the history of this world, and something that will shape it again. The forces that govern the Oort Cloud are not the ones that govern the inner solar system. In the neighborhood of the planets, the sun is everything. Its gravity organizes every orbit, sets every speed, determines every trajectory. A comet that wanders into the inner solar system feels the sun's pull more powerfully with every passing week, accelerating inward, swinging around, and then racing back out. The sun is the undisputed authority in that region, and everything that happens there happens by its rules. But the Oort Cloud exists at the edge of the sun's reach, in a zone where that authority is genuinely contested. Out there, at distances of tens of thousands to 100,000 astronomical units and beyond, the sun's gravitational pull has weakened so dramatically that other forces can compete with it and sometimes win. There are two great disturbers of the Oort Cloud, two mechanisms that reach into that frozen shell and pull things loose, and understanding them is essential for understanding why the cloud is not merely distant, but genuinely, actively dangerous in ways that operate on time scales human beings can barely conceive. The first is the galaxy itself. The Milky Way is not an inert backdrop. It is a structure of enormous mass, hundreds of billions of stars, vast clouds of gas and dust, dark matter extending far beyond its visible edge, and like all massive structures, it exerts gravitational forces on everything within its reach. These forces do not act the way the sun's gravity acts, pulling things cleanly toward a central point. Galactic gravity acts as a tide. Think of the way the moon's gravity does not simply pull all of Earth's oceans toward it uniformly, but instead deforms them, creating a bulge on the side facing the moon and a corresponding bulge on the opposite side, while the water at the equator is pulled slightly outward by the imbalance. The result is something that moves and shifts in response to a gradient rather than a single pull. The Milky Way does the same thing to objects in the outer solar system and at the distances of the Oort Cloud, where the sun's authority has been weakened to a whisper. The galactic tide is powerful enough to meaningfully reshape orbits over millions of years. The galactic disk, the flat, populated plane of the Milky Way where most of its stars and gas reside, exerts a compressive tidal force perpendicular to the disk plane. Objects in the Oort cloud that orbit above and below that plane feel this compression, which gradually alters the shape and orientation of their orbits. What begins as a nearly circular orbit can, over millions of years of tidal squeezing, become more elongated, its closest approach to the Sun gradually dropping inward. When that closest approach, called the perihelion, drops far enough into the realm of the giant planets, Jupiter and Saturn catch the object gravitationally and either eject it entirely or redirect it into the inner solar system. The galactic tide is, in this sense, a slow-motion comet delivery system, grinding away at the outer edges of the Oort cloud, continuously, and sending a steady trickle of objects inward on journeys of tens of thousands of years. Scientists estimate that up to 90% of all comets arriving in the inner solar system from the Oort cloud may owe their trajectory to the galactic tide. This is not a dramatic event. It is not a sudden catastrophe. It is a permanent, continuous process operating across geological time, reshaping the Oort cloud slowly and persistently in the same way that water reshapes a canyon. The comets we see from Earth, the ones that develop their brilliant tails and grace the night sky for weeks or months before disappearing outward again, are, most of them, the product of this process. The galaxy is, in a sense, throwing things at us. Not maliciously, not with any intent, but as an inevitable consequence of the mathematics of gravity operating at scale. This matters for exploration in a specific and underappreciated way. Any spacecraft that ventures into the Oort cloud does not enter a static environment. It enters an environment that is in constant, slow-motion motion, an environment where orbits are being altered continuously by forces that cannot be predicted from within the cloud itself, because those forces depend on the distribution of mass throughout the galaxy, which is not known with the precision needed to compute every individual trajectory. A navigation computer aboard a spacecraft in the inner solar system can predict where an asteroid will be years or decades into the future with remarkable accuracy, because the system is relatively simple. The Sun dominates, the planets perturb things predictably, and the math is manageable. A navigation computer in the outer Oort cloud would face an environment governed by galactic forces that vary across space in complex ways, applied to trillions of objects whose positions are mostly unknown and whose orbits are being slowly altered by forces that defy easy computation. The navigation problem alone would be of a different order of difficulty from anything in the history of spaceflight. The second great disturber is more dramatic, more localized, and in some ways more frightening: passing stars. The Sun is not fixed in the galaxy. It is orbiting the galactic center, completing one full orbit roughly every 225 million years, moving through a neighborhood of stars that are themselves in constant motion. Most neighboring stars pass one another at distances measured in light years, close enough by galactic standards, but far enough in real terms to have only the most negligible effects on planetary orbits and the inner solar system. The Oort cloud, however, extends so far that stars passing even a light year or two away can reach into it and disturb the objects on its outer edges, sending some of them off on new trajectories. These close stellar approaches happen regularly on geological timescales. Astronomers, using data from the European Space Agency's Gaia spacecraft, a satellite that has mapped the positions and motions of more than 1 billion stars with extraordinary precision, have been able to reconstruct which stars have passed close to the Sun in the past and which will do so in the future. The picture that emerges is of a solar system embedded in a slowly churning stellar neighborhood, punctuated periodically by encounters close enough to matter for the Oort Cloud. Most of these encounters are gentle nudges at interstellar distances, a star passing a light year or more away, disturbing only the outermost fringe of the outer cloud, sending at most a modest increase in comet arrivals to the inner solar system. But some encounters are closer. Researchers studying the Gaia data have identified a star whose predicted close approach stands apart from every other known encounter in the future and past history of the solar system, a star whose passage is projected to plunge it, not just past the outer edge of the Oort Cloud, but deep into the inner regions of the cloud itself. That star is Gliese 710. Gliese 710 is an orange dwarf star, not much to look at by stellar standards, roughly 60% the mass of the Sun, too dim to see, without a telescope at its current distance of approximately 62 light-years away in the constellation Serpens. It is not a remarkable star. Most people have never heard of it and never will, at least not in any lifetime presently alive. But the mathematics of its current position and velocity, computed from Gaia data with a precision several times better than anything available before the spacecraft launched, point to a conclusion that is difficult to look at calmly. In approximately 1.3 million years, Gliese 710 will pass through the solar system's Oort Cloud. The best current estimate of its closest approach is approximately 10,000 to 13,000 astronomical units from the Sun, well inside the outer Oort Cloud and reaching the outskirts of the inner Hills cloud. A separate 2026 study refined earlier calculations and arrived at a closest approach of approximately 12,800 astronomical units within that same range. Researchers Philip Bursky and Piotr Dybczynski, analyzing the Gaia data, described this encounter as the strongest disrupting stellar encounter known in the future and past history of the solar system. Their analysis found 100% certainty that Gliese 710 will pass within the outer boundary of the Oort Cloud, and concluded that the encounter will be approximately 20 times more gravitationally disruptive than any other stellar approach identified across the full 10 million year range their study examined. Let that settle for a moment. Not the most disruptive encounter in the next million years. Not the most disruptive in the past million years. The most disruptive in the entire 10 million year window of their analysis, past and future combined. What happens when a star of that mass passes at that distance through the outer Oort Cloud? The physics is well understood, even if the precise outcome cannot be predicted object by object. Gliese 710's gravity will reach into the cloud like a hand sweeping through loose sand. Objects near its path will have their orbits significantly altered. Some will be captured by Gliese 710's gravity as it passes, carried away with the star as it continues through the solar neighborhood. Others will be flung outward, ejected from the solar system entirely into the interstellar void. But a substantial fraction will be knocked onto new orbits that bring their inner turning points much closer to the Sun orbits that will, after the star has long since departed, deliver those objects into the inner solar system as a prolonged, elevated shower of long-period comets. The timescale of that shower is not days or years. It is millions of years. Current models suggest that the encounter with Gliese 710 could produce an elevated rate of comet arrivals in the inner solar system, lasting for millions of years after the flyby, a slow-motion cascade of objects arriving, one by one, on their long inward journeys, each one representing a fragment of the disturbance set in motion by that single stellar passage. From the inner solar system, an observer present during the peak of that shower might see 10 naked-eye comets per year, a sky unlike anything humans have ever witnessed, bright visitors arriving steadily enough that the concept of a rare comet would no longer apply. What proportion of those objects would strike the Earth is genuinely uncertain. Researchers have estimated that the probability of a large comet impact during the heightened period following the Gliese 710 encounter would increase measurably, though the odds of any single impact severe enough to threaten civilization within a given span of years remain statistically small, even during such a shower. The concern is not that the encounter with Gliese 710 will certainly end life on Earth. The concern is that it will substantially increase the rate of comet arrivals for an extended geological period, elevating the risk of impact events above what it is during quieter eras in the solar system's history. And this is one star, one known approach. The Gaia catalogue has identified numerous other stars that have passed within a few light years of the Sun within the past few million years, or will do so within the next few million years. Schultz's star, a dim red dwarf, is now believed to have passed through the outer Oort Cloud approximately 70,000 years ago, at a distance of roughly 52,000 astronomical units. It was too small and too distant to cause the same level of disruption as Gliese 710, but it almost certainly disturbed the outer cloud to some degree. The records of these encounters accumulate over geological time, each one stirring the cloud slightly differently, each one contributing to the slow, irregular rhythm of comet delivery to the inner solar system. There is also the possibility, not yet confirmed but seriously discussed in the scientific literature, that some of the mass extinction events in Earth's history may be connected to periods of elevated comet flux from the Oort Cloud, triggered by especially close stellar encounters, or by the passage of the solar system through denser regions of the galactic disk, where tidal forces and molecular cloud encounters are stronger. The extinction event 66 million years ago that ended the non-avian dinosaurs was almost certainly caused by an asteroid from the inner solar system. The Chicxulub impactor has been traced to an asteroid family, not a comet, but other extinction boundaries are less clearly explained, and some researchers have proposed that periodic comet showers from the Oort Cloud may have contributed to the pattern of mass extinctions visible in the fossil record. This remains a hypothesis rather than a confirmed conclusion, and the scientific community has not reached consensus on it. But the hypothesis is taken seriously, which tells you something important about how seriously scientists regard the Oort Cloud as a source of genuine biological consequence for this planet. Now add to all of this the problem that any exploring vessel would face when it enters this environment. The galactic tide and passing stars are not the only dangers. They are the macro-scale disturbers operating across the entire cloud over millions and billions of years. At the scale of a spacecraft trying to navigate through the cloud in real time, the danger takes a different form, and it is one that is harder to reason around because it does not announce itself. Every object in the Oort cloud is moving, not quickly. By planetary standards, orbital speeds at those distances are measured in meters per second, almost imperceptibly slow in the cosmic context, but moving nonetheless, in orbits that are not confined to any plane, arriving from any direction in three-dimensional space. The inner solar system is organized. The planets, the asteroid belt, the Kuiper belt, these all lie roughly in the ecliptic plane, the flat sheet of the original protoplanetary disk. When you are navigating in the inner solar system, you know where to look for things. You know that the most likely source of incoming hazards is in the plane of the planets, and you can scan that plane with appropriate instruments. The Oort cloud has no plane. Its objects orbit in all directions, at all inclinations, equally distributed across the sky. A spacecraft entering the outer Oort cloud would face potential incoming objects from above, below, ahead, behind, from any angle simultaneously. The density of objects per unit volume is, as described earlier, very low. The average separation between objects is tens of millions of kilometers. But at the speeds a spacecraft would need to be traveling to cover the distances involved in any reasonable mission timeline, tens of millions of kilometers of separation provides far less comfort than it might initially seem. A spacecraft traveling at 10 times the speed of Voyager, one would be moving at approximately 380,000 miles per hour, or roughly 170 kilometers per second. At that speed, an object 1 million kilometers away, 100 times the distance between Earth and the Moon, would be reached in less than 2 hours. A 10-kilometer wide comet nucleus, moving on an intersecting trajectory, undetected until the spacecraft was 1 million kilometers away, would allow a reaction time of roughly 90 minutes. That may sound like enough time for human decision-making, but the object would need to be detected first. In the darkness of the outer Oort cloud, where the sun provides almost no useful illumination, a black or very dark object and most cometary nuclei are extraordinarily dark. Reflecting only a few % of the light that strikes them would be essentially invisible to any instrument currently in operation until it was far too close for a meaningful course correction. Deep Space Network radar, which has been used to track near-Earth asteroids from the ground, operates effectively only within the inner solar system. At Oort cloud distances, it would be useless. A spacecraft would need to carry its own collision avoidance radar, scanning continuously, and the sensitivity required to detect a 10-kilometer object at a distance of several million kilometers in the absence of meaningful sunlight would require instrumentation beyond anything currently deployed. It is a solvable engineering problem in principle, but it has not been solved, and solving it is not a trivial undertaking. And even with the best conceivable radar, the sheer volume of the outer Oort cloud means that sustained scanning in all directions simultaneously would demand a computational and power infrastructure that no spacecraft in the history of human spaceflight has carried. The navigational danger is compounded by what happens if a spacecraft, attempting to avoid one detected object, moves onto a course that brings it closer to another undetected one. In the inner solar system, course corrections can be validated by ongoing ground tracking, by independent observations from Earth-based telescopes, by teams of navigators cross-checking each other's calculations against a continuous stream of updated position data. At Oort cloud distances, the one-way communication delay of months to years means that no course correction can be validated from Earth in any time frame useful for avoiding a collision. Every decision must be made locally, by the crew or by onboard autonomous systems, in real time, with no possibility of consulting the teams and models back on Earth that are best equipped to evaluate the options. It is a level of operational autonomy that no human space mission has ever been asked to maintain, sustained over years or decades, in an environment that cannot be fully characterized in advance. None of this means that a mission to the Oort Cloud is permanently inconceivable. Science does not work in permanence. What seems impossible in one century sometimes becomes routine in the next. But understanding the specific nature of the obstacles is the honest starting point for any serious discussion of what it would take. The obstacles are not primarily psychological or motivational. They are not primarily a matter of political will or funding. They are physical, written into the distances, the communication constraints, the navigational environment, and the power requirements of a region that is simultaneously 300 years away from our best current spacecraft and separated from Earth by communication delays measured in years. And there is one more layer to this. The Oort Cloud is not a sealed system. The same forces that send objects inward from the cloud also, on occasion, bring objects into the cloud from outside, from interstellar space, from the debris ejected by other solar systems as their own planetary systems formed and evolved. The Oort Cloud is, in a sense, a receiving zone as well as a reservoir. This became more than a theoretical possibility when, in October of 2017, astronomers detected Oumuamua, the first confirmed interstellar object ever observed passing through the solar system. Oumuamua was strange in almost every respect, elongated beyond any known solar system body, accelerating in ways that could not be fully explained by the sun's gravity alone. Almost certainly not a typical comet or asteroid by any classification then in use. It passed through the inner solar system on a hyperbolic trajectory, meaning it had arrived from beyond the solar system and was not gravitationally bound to the sun. It had come from interstellar space. And it was gone before detailed study was possible, departing at speeds no spacecraft could have matched with the technology of 2017. 2 years later, in 2019, astronomers confirmed a second interstellar visitor, this one unambiguously a comet, 2I Borisov, discovered by Crimean amateur astronomer Gennady Borisov. 2I Borisov was more cooperative than Oumuamua, arriving with sufficient advance notice and moving slowly enough that telescopes around the world were able to study it extensively. Its spectrum showed the presence of water and carbon monoxide ice, materials that matched what we see in solar system comets. 2I Borisov was a comet from another star, composed of materials that looked, in broad terms, remarkably like the materials in our own cometary population. It was a reminder that the chemistry of planet formation may be broadly consistent across star systems, that the ice and rock we call the Oort Cloud is not peculiar to our Sun, but likely a common feature of stellar systems throughout the galaxy. Then, in July of 2025, a third interstellar object was confirmed, 3I Atlas, discovered on the 1st of July 2025 by the Asteroid Terrestrial Impact Last Alert System telescope operating in Chile. 3I Atlas is an active comet. It was producing a coma and tail as it approached the Sun, and its trajectory was confirmed by astronomers worldwide to be hyperbolic, meaning it had arrived from outside the solar system. It is only the third interstellar object ever observed, and its discovery confirmed that these visitors are not vanishingly rare events, but rather the expected result of a universe full of solar systems, each ejecting material into the interstellar medium, with that material occasionally passing through our neighborhood. What this means for the Oort Cloud is significant. The cloud sits at the outer boundary of the solar system, where the sun's gravitational grip is at its weakest and where incoming objects from interstellar space first encounter the solar system's gravity. Objects arriving from other stellar systems at modest relative velocities, slower interstellar visitors, might actually be captured by the sun's gravity at Oort Cloud distances and incorporated into the cloud itself. Over billions of years, the Oort Cloud may have accumulated a fraction of material from other solar systems, mixed in with the sun's own primordial leftovers, indistinguishable in appearance from the native population. Studying Oort Cloud objects up close would mean, in principle, studying a sample that potentially includes interstellar material chemistry from other suns, preserved in the same frozen quiet as our own. This makes the Oort Cloud simultaneously one of the most scientifically valuable places in the solar system and one of the least accessible. Its scientific value grows precisely because of its pristine nature, its enormous age, and its possible interstellar mixing. Its inaccessibility grows from the same distance, the same cold, the same darkness that preserved it so perfectly for so long. You cannot have one without the other. The Oort Cloud is valuable because it is unreachable. And it is unreachable in ways that compound one another: distance, communication delay, navigation in an uncharted environment of radially omnidirectional hazards, power constraints at solar distances where no panel has ever been designed to operate, and the constant, continuous background of galactic and stellar perturbation that reshuffles the environment on timescales ranging from the very slow to the catastrophically sudden. When Gliese 710 arrives in 1.3 million years, it will not be the end of the story. It will be one chapter in an ongoing history of stellar encounters that have been disturbing the Oort Cloud for 4.6 billion years. It will be the most disruptive chapter in any span of time that science has yet been able to examine. But it will not be unique in kind, only in degree. The stars have always moved through the neighborhood. The galaxy has always pulled. The cloud has always responded, slowly, over millions of years, sending its frozen messengers inward on journeys that carry within them the record of those disturbances. What we have not yet been able to do, and what remains one of the great open challenges of planetary science, is study those frozen messengers up close before the sun has had a chance to alter them, to intercept one on its very first pass, when its surface is still the surface it has carried for billions of years, before the warmth of the inner solar system has driven off the most volatile ices and reshaped the body we are trying to read. That challenge is the next chapter of this story, and the missions designed to address it are among the most ambitious, most carefully planned, and most scientifically freighted efforts now underway in the history of space exploration. The dream of intercepting a pristine comet from the Oort Cloud before the sun has had a chance to alter it is not new. Planetary scientists have been articulating that goal for decades, because what such a comet carries within its surface layers is irreplaceable. Every comet that has passed through the inner solar system more than once has been changed by the experience. The sun's heat drives off the most volatile ices on the outermost layers, leaving a processed residue that tells us something about cometary chemistry, but not the full original story. The interior of a recurring comet is better preserved than its surface, but the interior is not accessible to remote sensing instruments. What scientists need is a comet on its very first approach, a body whose outermost millimeters have been kept in a refrigerator 4.6 billion years old and are now, for the first and probably only time, being exposed to sunlight. The challenge is timing. Long-period comets, the ones most likely to be arriving from the Oort Cloud for the first time, have orbital periods measured in thousands to millions of years. They spend almost all of that time in the deep cold of the outer solar system, and they arrive in the inner solar system on their own schedule, without announcement. A comet visible in Earth's skies last made its closest approach to the Sun during an era of human prehistory, or before any human being existed at all, and will not return until a civilization that may bear no recognizable relationship to ours is watching the same sky. You cannot build a mission to intercept a comet if you do not know which comet to target until a few months before it reaches the inner solar system. The spacecraft would need years to reach the comet, and years do not compress into months, no matter how urgent the science. The solution that ESA devised is elegant in a way that only the best mission designs tend to be. Do not wait to know the target before launching. Launch the spacecraft to a waiting position in space. Park it where it can respond quickly when a suitable comet is identified, and let it wait. The mission is called Comet Interceptor. As of early 2026, it has passed its critical design review, completed in December of 2024, and the Science Program Committee of ESA approved an earlier launch window than originally planned, now targeting the period between August of 2028 and July of 2029. It will share its ride to space with ESA's aerial exoplanet mission and will be delivered to the Sun-Earth Lagrange Point 2, a gravitationally stable position approximately 1.5 million kilometers behind Earth as viewed from the Sun, where it will park in a halo orbit and wait the Vera C. Rubin Observatory in Chile, which began its full sky survey operations in 2025, is expected to dramatically increase the rate at which pristine comets from the outer solar system are detected while they are still far from the Sun, while they are still, in some cases, beyond the orbit of Saturn. That additional detection time is what makes the Comet Interceptor concept work. If a suitable target is identified while Comet Interceptor is at Lagrange Point 2, the spacecraft has enough propulsion capability to depart its parking orbit and intercept the comet as it makes its inbound journey. The updated mission design, with the earlier launch window, increased the available fuel load enough to raise the delta-V capability. The total velocity change the spacecraft can apply from approximately 600 meters per second to approximately 1,000 meters per second, substantially improving the probability of finding and reaching a suitable target during the mission's operational lifetime. Comet Interceptor is not a single spacecraft. It consists of 3 modules: a primary spacecraft carrying the main science payload, and 2 smaller probes, one built by ESA and one provided by the Japan Aerospace Exploration Agency as part of a collaboration that mirrors the international character of modern planetary science. When the target comet is close enough, the 3 modules will separate and make simultaneous observations from multiple positions around the comet, one in front of it, one behind, one to the side, creating a 3-dimensional profile of the comet's nucleus, its surrounding coma, and the gas and dust environment it generates as it warms for the first time. No comet has ever been studied from 3 simultaneous vantage points. The technique will reveal spatial variations in the comet's activity places where outgassing is more intense, regions where the surface is different in composition or texture from neighboring areas that a single spacecraft flyby could never detect. What will Comet Interceptor find? Nobody knows, in the specific sense, but the scientific community has a strong expectation that a dynamically new comet, one arriving from the Oort Cloud for the first time, will show surface chemistry that differs from what has been found on short period comets studied by previous missions. ESA's Rosetta mission, which orbited the comet called 67P Churyumov-Gerasimenko from 2014 to 2016, found a body of extraordinary complexity: cliffs, boulders, smooth plains, steep valleys, active jets of gas and dust erupting from specific surface regions, and a composition rich in organic molecules, including some amino acid precursors. But 67P Churyumov-Gerasimenko has orbited the Sun countless times. Its surface has been reshaped by those repeated passages. It is a survivor, not a newcomer. A comet from the Oort Cloud, arriving on its first pass, may look quite different. Its surface may carry ice that has never sublimated, organic compounds in configurations that have never been disrupted by heat, and structures that formed in the early solar system and have been maintained by 4.6 billion years of cold storage. Whether those differences will be dramatic and immediately obvious, or subtle and requiring careful analysis to reveal, is one of the genuinely open questions in cometary science. The Comet Interceptor mission was designed precisely to answer it, or to begin answering it, because one mission intercept of one comet is a data point, not a census, and the science it produces will undoubtedly raise as many questions as it settles. The scientific value of that data point is hard to overstate. One of the deepest unresolved questions in the study of our solar system's history concerns the delivery of water and organic molecules to the early Earth. The current scientific understanding is that the early Earth was too hot and too close to the Sun for the water and volatile organic compounds that define terrestrial life to have been part of the original planet. Much of that water and many of those organic building blocks were likely delivered from the outer solar system through impacts by comets and water-bearing asteroids during the period known as the Late Heavy Bombardment, roughly 3.9 billion years ago, when the inner solar system was still being pounded by leftover material from the outer regions. Comets from the Oort Cloud are among the most chemically rich objects in the solar system repositories of exactly the kinds of water, ice, and carbon-bearing compounds that may have seeded the chemistry of life on Earth. Understanding what a pristine Oort Cloud comet is made of before the Sun strips away its outermost layers means understanding something closer to the original chemical package that the early Earth may have received. This is why the Comet Interceptor mission carries instruments designed to analyze the comet's chemical composition in detail spectrometers that can identify specific molecules in the gas and dust being driven off the prongs. Surface cameras that can map the nucleus at resolutions fine enough to distinguish geological features. Dust analyzers that can characterize the size, distribution, and composition of particles in the coma. Each instrument asks a slightly different question about the same object, and together they are designed to build as complete a picture as a flyby which will last only a matter of hours at most can produce. That constraint hours of data collection at a target that has been traveling for potentially millions of years is itself a reminder of the fundamental disproportion between the scale of what the Oort Cloud holds and the scale of what any mission in the foreseeable future can access. Comet Interceptor will not enter the Oort Cloud. It will not travel to the source. It will intercept one messenger. As that messenger crosses the Earth's orbital region, study it for a matter of hours, and then watch it continue outward and away. The cloud itself will remain exactly as it is, unchanged, unreached, holding its trillions of frozen bodies in the same dark cold it has maintained since the solar system was young. There is something quietly affecting about that reality, if you let yourself sit with it. The Oort Cloud has been there for the entire history of the human species, and for the 4+ billion years before that. It surrounded the solar system when the first single-celled organisms appeared in Earth's oceans. It surrounded the solar system when those organisms slowly, over hundreds of millions of years, evolved into multicellular forms, when the seas filled with the ancestors of everything that now lives on land, when the first forests grew, when the first land creatures developed. It surrounded the solar system when the dinosaurs flourished for 160 million years and were ended in a geological instant by an impactor from the inner solar system. It surrounded the solar system when the first members of our genus stood upright on an African savanna and looked up at the same night sky we look at tonight. In all of that time, the Oort Cloud itself did not change in any fundamental way. Individual objects were perturbed and sent inward. Stellar encounters nudged portions of the cloud's population onto new paths. The galactic tide slowly shifted orbits over millions of years. But the cloud as a whole, its vast spherical structure, its reservoir of frozen primordial material, its occupation of the outermost reaches of the solar system, persisted through all of it. It will persist for the foreseeable future. It will be there when Gliese 710 makes its close passage in 1.3 million years, shaking a portion of the outer shell loose and sending waves of comets inward over the following millions of years. It will be there when those comet showers gradually subside and the cloud settles back into its long quiet. It will be there, in all likelihood, for billions of years beyond even that, until the sun itself eventually expands into a red giant and the inner solar system is engulfed, and even then, the Oort Cloud, at its enormous distances, may survive the transformation largely intact, drifting away from a cooled stellar remnant into the dark of the galaxy. We are living in what is, by any honest reckoning, the very earliest moment of humanity's awareness of this place. 76 years have passed since Jan Oort published his 1950 paper and gave the scientific world its first coherent framework for understanding what surrounds us at those enormous distances. In that same 76 years, we have gone from no human-made objects in space at all to Voyager 1 crossing the heliopause and entering interstellar space. That is a breathtaking arc of progress by the standards of any previous era. But that same Voyager 1, the greatest distance any human technology has ever achieved, has not yet covered 9% of the distance to the inner edge of what Oort described. Progress in space exploration has always moved faster than the timescales of the universe demand, and slower than human impatience would prefer. The gap between those two truths is where most of the real history of science is written, in the patient accumulation of knowledge, each step revealing the scale of what remains, each answer producing a more precisely articulated question. The Oort Cloud exemplifies this better than almost any other subject in all of astronomy. We knew comets existed for as long as we have kept records. We began to understand their composition only in the 20th century. We understood their origin tentatively, indirectly, only in 1950. We are only now building the first mission designed to catch one of them before the Sun has altered its most pristine surface. And we have not yet sent so much as a probe to the outer solar system with the explicit goal of reaching the cloud's inner boundary, much less the cloud itself. But knowledge about the Oort Cloud has advanced through avenues other than direct spacecraft observation, and those avenues are worth tracing because they reveal how much can be understood about a place no one has visited. The study of long-period comets has produced a detailed statistical picture of the cloud's size, structure, and population. Computational simulations of the early solar system have yielded increasingly refined models of how the cloud formed and how it has evolved over 4.6 billion years. The Gaia spacecraft's comprehensive survey of stellar motions has given astronomers an unprecedented ability to identify past and future close approaches by neighboring stars and to model how each of those approaches has altered or will alter the cloud's population. The arrival of 3I Atlas in July of 2025, only 3 years after 2I Borisov's detailed study, has begun to establish that interstellar comets are a recurring feature of the solar neighborhood, not a once-in-a-generation rarity, and has prompted new thinking about how often the Oort Cloud's population may be supplemented by material from beyond the solar system. The Vera C. Rubin Observatory's decade-long legacy survey of space and time, which began operations in 2025, is projected to roughly double the number of known Oort Cloud comets in its first few years alone. Before that survey, the number of known comets believed to originate from the Oort Cloud stood at approximately 4,500 objects. Doubling that catalogue means doubling the statistical sample from which scientists can infer the cloud's structure and population. More objects means more orbital data, more precise clustering of aphelion distances, more refined estimates of where the cloud's inner and outer boundaries lie, and more opportunities to identify the most pristine appearing candidates for eventual interception. The Rubin Observatory's contribution to Comet Interceptor's mission is particularly direct. The earlier Comet Interceptor is positioned at Lagrange point 2. The more of the Rubin Observatory's early survey results it will be in place to respond to. The synergy between the two programs reflects a broader shift in how planetary science now approaches the Oort Cloud, not with a single transformative mission, but with an interconnected network of observational and spacecraft capabilities, each designed to compensate for the limitations of the others, each adding a layer to a picture that was almost entirely invisible just a few generations ago. What does all of this mean for humanity's relationship with the Oort Cloud going forward? It means that the next chapter of Oort Cloud science will be written not by crossing the distance to the cloud, but by extracting as much knowledge as possible from the messengers the cloud sends to us. Every new long-period comet detected by the Rubin Observatory is an opportunity. Every interstellar visitor confirmed by astronomers worldwide is a piece of comparative data. Every flyby or eventual rendezvous mission to a freshly arrived Oort Cloud comet is a sample analysis conducted at 300 million kilometers of remove from the source. The cloud itself will remain unreachable on any human timescale, but the signals it sends, the frozen bodies it dispatches, the trails of dust and gas they leave behind as they approach the sun for the first time are reaching us constantly, and we are finally becoming sophisticated enough to read them. There is something to sit with here, something that the entire journey of this video has been slowly building toward. The Oort Cloud is the outermost boundary of the solar system in the sense that matters most. It is the limit of the Sun's gravitational authority. Beyond it, no object owes its orbit to the Sun. Beyond it, the galaxy governs everything. The Oort Cloud is the last place where, if you are drifting in the cold and the dark, you can still say that you are, in some meaningful technical sense, within the solar system, within the reach of the same gravitational order that holds the Earth in its orbit, that keeps the Moon in its circuit around the Earth, that has organized the planets and their moons and the asteroid belt and the Kuiper belt into the nested, intricate structure that has provided a stable home for life for billions of years. And it is so far away that the most successful spacecraft in human history, traveling without stopping for nearly 50 years, has not yet covered 9% of the distance to its inner edge. This is not a melancholy observation. It is, if you take a moment to consider it properly, one of the most clarifying facts in all of science, because it reveals something true and important about the proportion between human ambition and the actual scale of the universe. We are very small. We have always been very small. The solar system is far larger than most people ever have occasion to realize, and the Oort Cloud is the proof. Everything we have done, every rocket launched, every orbit achieved, every planet and moon visited, or photographed, or characterized, has taken place within the innermost fraction of the solar system's true extent. The Oort Cloud has been watching all of it from a distance that our fastest vehicles would take centuries to cross. And yet, we know it is there. We know roughly where it starts and where it ends. We know approximately how many objects it holds. We know what those objects are made of. We know what disturbs them and how they fall inward when they are disturbed. We know that it formed 4.6 billion years ago from the same raw material as the planets, and that it has been preserved at temperatures within a few degrees of absolute zero ever since. We know that it is not just our solar system that has such a cloud, that the same dynamics that created the Oort Cloud around our Sun almost certainly operate around other stars throughout the galaxy, and that the interstellar comets we have begun to detect are evidence of those other clouds exchanging material across the spaces between stellar systems. We know all of this without ever having sent a single spacecraft to the cloud itself. We have read it entirely from the evidence it sends to us, from the orbits of comets, from the motions of stars, from the mathematics of gravity applied at solar system scales, from the patient and precise work of astronomers who spent careers analyzing data that pointed towards something they could not see. Jan Oort did it from the orbital histories of 19 comets. The scientists who followed him did it from catalogues of hundreds, then thousands. The scientists at work today are doing it from the data streams of space observatories that see the whole sky every night. The Oort Cloud remains the most dangerous place in the solar system to explore, for all the reasons this video has traced in careful detail. The distance that defeats every spacecraft, the communication delays that would sever any crew from Earth more completely than any ocean ever separated any sailor from home, the navigation environment of invisible objects arriving from all directions in a darkness too deep for any instrument to fully scan, the galactic tidal forces that reshape orbits invisibly over millions of years, the stellar encounters that can stir the cloud into episodes of elevated cometary flux lasting millions of years, sending waves of frozen objects inward on trajectories that intersect, occasionally, with the inner planets. All of these are genuine, specific, Physics-rooted obstacles, not engineering challenges waiting for the right technology, but fundamental constraints of time and space that do not yield to ambition alone. But dangerous is not the same as forbidden, and unreachable on current timescales is not the same as unreachable in principle. Science has a long memory and a longer patience, and the Oort Cloud will still be there when whatever comes after us has the means to cross the distance. In that frozen shell, held in place by the last whisper of the sun's gravity and the patient pull of the galaxy, the original materials of the solar system are waiting unchanged, undisturbed, the oldest cold storage archive in the known history of our corner of the universe. That is the Oort Cloud, the most distant place that is still, in any meaningful sense, ours. Sleep well, traveler. The frozen edge of the solar system keeps its ancient silence just for us.